Now we want to look at probability distributions for a continuous random variable x. And the way you calculate these probabilities is a lot different than how we do discrete random variables. The reason that is because we have to specify these random variables by a curve that's called a density curve. And that density curve is defined by a function, f of x, and that function is called the density function. And the density function represents the probability of these values. But the problem is, we can't look at the probability of a single value in a continuous random variable. It can be any number of values, and so we can't isolate a single value. So we have to look at this continuous function that's obtained using mathematical modeling. And instead of looking at individual probabilities, we're going to have to look at probabilities over an interval. And in order to do that, we're actually going to calculate the area under this curve. So the probability is represented by the area under the curve. Sometimes probability is going to be as simple as looking at the area of a rectangle, or maybe the area of a triangle, if the density function can be described using rectangles or triangles. Other times, the probability is going to be a shape that we don't know how to find the area for, and without calculus, we'll have to rely on computer software or tables provided in our textbook. But a few properties here with density functions is that the values for the function have to be greater than or equal to 0, has to be at least 0, and the total area under the density curve is going to be equal to 1. No matter what the shape is, the total area will be equal to 1. We're going to be looking at 3 different types of events. We're going to be looking at a between event. And so that's where we're looking for the probability that the outcome is between 2 events, or 2 values, A and B. Or maybe we're going to be looking for the probability that x is less than some value A. And so we'd be looking at the area below A. Or maybe we're looking for the probability that x is larger than some value B. And so here we would be looking for the area to the right. For the distribution that I drew here, the normal distribution will not be able to calculate the area of that shape using formulas from geometry, but we will learn in the next section how to calculate these types of probabilities. In this section, we'll actually be able to calculate all of these probabilities just using geometry. A note here on continuous random variables, the probability that x equals some specific number is actually 0. And I know that's a hard concept to understand because that x value does take on a particular value. But I want you to imagine all the sand in the world, and you were trying to identify a single grain of sand. You could spend your whole life and never get close to finding that single grain of sand. And that's the case here. Every particular value represents one little grain of sand out of all the values or all the locations of all of the sand pieces. And so you're never going to find the value that you're looking for. And so it doesn't matter if you are going to have x between A and B where you include A and B, or maybe you don't include A but you do include B, or you include A not B, or you don't include either endpoint. It doesn't matter. Those endpoint values are statistically impossible, and so the probabilities will all work out exactly the same with these continuous random variables. That was not the case with discrete random variables, because they did take a particular value and there was a finite number of them. But here we have an infinite number of possible values that this can take.